All right, let's jump right in. Every single day, you and I, we navigate this world that's guided by all these invisible systems, right? I'm talking about the digital maps that tell us where to go, how to get there, and what to expect on the way. But behind that simple little blue line on your phone, there is some seriously powerful science at play. So today, we're going to pull back the curtain on the hidden world of network analysis.
I mean, really stop and think about that for a second. It's not just a flat picture of the roads, is it? No way. It's this intelligent system that actually understands traffic and turns and time. The secret? Well, it lies in treating our world not just as a map, but as one massive interconnected network.
Okay, so to really get how this all works, we first need to lay out the blueprint. We gotta ask the basic question: what exactly is a network in the world of Geographic Information Systems, or GIS?
You know, at its heart, a network is actually super simple. It's just a collection of lines, which we call edges, and the points where they all connect, which we call nodes or junctions. Just think of it like a digital skeleton for anything and everything that flows, from cars on a highway to water running through a pipeline.
And this image here, it's the perfect example. These networks are literally everywhere you look. We see the roads in gray, a river snaking through in blue, a railroad in red. Now, each one of these is its own distinct network with its own unique rules, but they're all built on that exact same fundamental idea of edges and nodes.
And this is where things start to get really smart, because, let's be real, a simple drawing of a bunch of lines isn't going to cut it. To be actually useful for analysis, the network has to understand the rules of the real world it's supposed to represent.
For instance, can you travel one way or two ways? A river is the perfect example of what we call a directed network. The water only flows downhill, right? But a normal street is usually undirected, meaning you can travel in both directions. And that little distinction, it is absolutely crucial for any kind of routing calculation.
Okay, and then there's this concept called impedance. It sounds a little technical, I know, but all it really means is the cost of traveling through a part of the network. And that cost isn't always distance. It could be time, which is affected by things like speed limits, or it could be restrictions, like a no left turn sign. This is exactly how the network starts to act like the real world. So now that we've got the blueprint down, let's open up the toolkit. Let's see how these concepts build into tools that solve real, actual problems, starting with the most famous one of all. The number one job, the thing network analysis is used for most often, is finding the shortest path. But here's the trick. Shortest is a really flexible word. For an ambulance, shortest definitely means the fastest route. But for a shipping company, it might mean the least distance to save on fuel, or maybe even the route that costs the least amount of money in tolls. And this map right here just illustrates that concept perfectly. That red triangle, think of it as a single starting point, maybe a fire station or a warehouse. The blue lines are the calculated shortest paths to a whole bunch of different destinations. An algorithm, like the famous one from a guy named Dijkstra, can solve this incredibly complex puzzle because it's smart enough to test the closest options first, finding the absolute best route almost instantly. It's kind of like magic. Okay, but routing from point A to point B is just the beginning. Things get way more complicated. What happens when a delivery driver has 100 or even 200 packages to deliver? Well, that brings us to a classic, and I mean classic, puzzle in computer science and logistics, the traveling salesman problem. This quote really just nails the problem, doesn't it? The goal is to find the shortest tour possible that hits every single customer and then gets you back to where you started. And what's so wild about this problem is that it gets exponentially harder to solve with every single new stop you add to the route. And for a real-world delivery driver, the best route is the super complex calculation. You're not just thinking about the shortest distance, you're juggling travel time, maybe you're prioritizing stops that have a higher demand, and at the end of the day, you're just trying to structure the route to get as many packages delivered as you possibly can. Okay, so here's the thing. This is about so much more than just your daily commute or your Amazon delivery. This technology is literally used to design the very communities that we live in. So far, we've been talking about navigating the networks that already exist, but some of the most powerful uses of this stuff are in planning and designing new things. This is where we get into ideas like location allocation, which is all about figuring out the absolute best place to put our most important resources. I mean, think about it from a city planner's perspective. You have to ask this huge life or death question.
By using network analysis, they can model thousands of potential spots to find that one single location that minimizes the travel time for firefighters to get to every single corner of the community. This isn't just cool tech, this is a life-saving tool.
And the really cool thing is, the process to solve a problem like this is actually pretty straightforward. It's almost like a four-step recipe. First, you build the digital network of streets. Second, you layer on all those real-world rules, the impedance we talked about earlier. Third, you clearly define what you're trying to achieve. And finally, you just hit go and let the computer do all the heavy lifting.
And this is where things get really mind-blowing, because this entire way of thinking, in terms of networks, is starting to break out of the world of just maps and geography. It's going everywhere.
It turns out that this simple, fundamental concept of nodes and edges, dots and the lines connecting them, it's a universal model. It's a ridiculously powerful way to understand nearly any complex, interconnected system you can possibly think of. I mean, just look at this list. It's wild. We're talking about microbiologists using this to map how a disease spreads from person to person, or criminologists analyzing the likely routes a criminal might take. Even neurobiologists are using this exact same thinking to map the trillions of connections between neurons and the human brain. It's the same core idea of nodes and edges, just applied in these radically different and unbelievably powerful ways.
Which really just leaves us with one last, fascinating thought to chew on. We've seen how this incredible tool helps us understand the flow of physical things through a city. But what happens when we start applying that same kind of thinking to things that are intangible? It really makes you wonder, what other invisible maps will we be designing next?